Well, good morning, everyone, and welcome back. This is the course on environmental bioethics within the program of Bioethics, Master of Science in Bioethics here at St. Thomas University. As always, we begin with a little prayer in the name of the Father, the Son, and the Holy Spirit. Blessed Trinity, we love you, we adore you, and we thank you once again for all your many blessings, for the gift of life, and for having us here today. We ask your inspiration, Lord, so that we may go deeply into the study of nature, of your creation that surrounds us, so that we may care for it, protect it, and leave something for those who come behind us, who come after us. May they appreciate your gift of life and nature, and ultimately call us to eternal life with you. We pray always for those who are in most need of your divine mercy at this time. In the name of Christ our Lord. Amen. Any questions or comments from previous lectures or anything on the program? No? At the end, I'm going to devote some time to strategizing a little bit for the biostatistics course, okay? So if you have any questions or comments there, hold them till I finish this session, and then we can get into that for those who are interested. Okay, so recapping a little bit, this one is on environmental bioethics. And so before we do the bioethical analysis, as always, we need to look at the environment itself, nature, simply because from the Catholic perspective, whenever we do bioethics, we call it, it's evidence-based. In other words, we allow nature to tell us what's going on, and then from there we do the ethical analysis as such, okay? So remembering that in the previous couple of lectures, the first one was dedicated mostly to the study of the Earth itself, how we came about with that theory of accretion, right? And then to be more specific, we call it inhomogeneous accretion. These are big words, just fancy words for processes that happen in the universe. I think there's a double C here on accretion, no? Right? All right. So accretion is the formation of planets as such, as they gather material throughout the universe by condensing and then gravity acting and pulling in more and more material. We can look at the moon as an example, because the moon has been around as long as the sun has been around. And if you notice, the surface of the moon is totally bombarded, right? We should have the same bombardment. And we did, as a matter of fact, until we developed an atmosphere. And so this is accretion is pulling in material, mostly from gravity, at very high speed, very hot. The numbers are truly astronomical when we consider the events that go on there. But what is inhomogeneous, the adjective, inhomogeneous, non-homogeneous, right, is that it has created several layers, generated several layers, the core, the mantle, the crust, generally, globally. And so the core is estimated to be as hot as the surface of the sun, which nothing could possibly live there as we know organic life today, right? But by the time we get to the crust, then we have the temperature is cooled down enough to maintain what? One molecule that is the basis of organic life. Water, right? Water, which by the way is inorganic, because for it to be an organic molecule, it needs to have carbon and hydrogen. But this one only has hydrogen, so it's an inorganic compound, and yet it is the basis, the foundation for life, essentially because metabolism, if we look at life at the organic level, you can talk about metabolism, right? At the cellular level, cellular metabolism, cellular respiration, and all the processes that happen there, and at the level of the whole body, organismal metabolism, body functioning, what we call body functioning. And that body functioning, that metabolism happens within what? It's a what? It's a soup. It's a soup. It's a dynamic soup of chemical reactions, all right? So it happens in liquid water. That's what we need, water in its liquid state, which is a very narrow range of temperature in centigrades between 0 and 100. And that's precisely how that scale, that Celsius or centigrade scale, is set precisely from 0 to 100. It's not, it's on purpose. That's precisely defines the liquid state of water, all right? Water being what is known as the almost universal solvent. Most substances dissolve in water. And what doesn't dissolve in water? Typically, what doesn't dissolve in water? Lipids, fats, oils, right? Greases, right? Those typically dissolve in alcohol, and then that mixture, alcohol with the lipids, dissolve in water, all right? It polarizes those molecules. So just to say, highlight again the importance of water in its liquid state, because there's plenty of other water in frozen or gas state in our planet and in other planets. But for life, there is that little window of opportunity, if you will, as they say in the business world. So anyway, that then we're concentrating on the lithosphere, on the crust of the Earth, that very thin layer of surface that allows us to live. And when we look at that life that occurs there, we see these three spheres, if you will. There is the lithosphere, which is the rock. Then there is the atmosphere, a very thin layer of gas that is benevolent for life. It wasn't always that way. Remember the primitive atmosphere, methane, and other gases that are toxic. But today we have a benevolent atmosphere to be able to respire, and also the CO2 necessary for photosynthesis. That's the atmosphere. And then, of course, the water, which is the vast majority of the surface of the Earth, is water, by surface and by volume. You'll see what I mean by that in today's lecture. Okay, so those are the three big spheres, if you will: lithosphere, atmosphere, and hydrosphere. And that's together, that is the ecosphere, is the living things, the living organisms, all the species that live on Earth, together with their physical properties, the abiotic factors that we call, right? Okay, so moving forward then, today, so we have talked about it, the lithosphere already, geophysics, how the Earth came about, and the crust itself. Then we talked about the atmosphere last lecture. Today is devoted to the hydrosphere, right? And just since we're here looking forward from here, the next lectures, we're going to be looking at energy transfer, how energy goes through the Earth, which is because all these things, if you look at it, are matter, material. But the other component, if you will, of the universe is energy, right? Matter and energy that interact in a dynamic way so as to allow for the possibility of life. So we have not looked at energy in detail yet. We'll devote a whole lecture to that, how the transfer of energy goes through the Earth, allowing for life to occur as such. Okay, so hydrosphere. Any questions, comments? You with me? Yeah? Let's look then at this issue of water, and mostly liquid water on Earth in its complex dynamic state as it goes through the Earth. So we have to look at some of the physical and chemical properties of water as such, of the molecule, at the molecular level. Then that would be kind of theoretical, because we just don't have individual molecules of water just lying around, all right? They're interacting in a very dynamic state in natural phenomena that are the rivers, the lakes, the oceans. These are the three main areas. Well, I guess we should put in here also the ice caps, because that is also water. Let me add there. Whoops. Ice caps. because even though the ice caps are definitely solid water, there's also life occurring there, right? Then currents, again, this is a very dynamic state. So oceanic currents, the big current patterns throughout the whole world, considering that most of the water on Earth is precisely in the oceans. The vast majority, over 90% of the water is in the oceans by volume. Okay, I have ice caps and glaciers here, the dynamics that are occurring in solid water, massive solid water moving around. Glacial and interglacial periods, which is going to set the foundation then for later talking about global warming and climate change, and the possible human factor influencing climate change. And then I'm going to end with the natural right to water, to potable water, meaning drinking water, and some papal documents, because it turns out that all recent popes have talked about the right to water and to drinking water because necessary for life. So let's get on with it. Here's a water molecule represented in this ball formation, okay, or sphere formation. What do I mean by the fact that water is a molecular magnet? What is the chemical formula for water? H2O, right? H2O, I should put it in here somewhere. And I need a subscript for a moment. Let me see, give a minute. I need one subscript. That's just to put a 2. And then get out of there. Back to unselect and the oxygen. Okay. Now, here's the oxygen. And because oxygen has 2 free spaces on the second orbit, don't worry about the atomic structure, it allows for 2 hydrogens to bind and bond. So here are the 2 hydrogens, but you notice that they're not equatorial on the molecule. The 2 hydrogens are not equatorial, they're off center. Either the North Pole or the South Pole, doesn't matter, but they're slanted off, okay? Because they're both positive, but then it distributes the charges so that there will be a negative charge on one end of the molecule and then 2 positive charges at the other end of the molecule. This is because of the molecular dynamics of how hydrogen bonds with oxygen, how 2 hydrogens bond with oxygen, okay? Has to do with the orbits, the electrons orbiting around the electrons of the hydrogen orbiting around the oxygen, the proton of the oxygen. Anyway, I'm not asking you to be responsible for the atomic description of this, but rather the molecule as a whole. You notice that the molecule is slanted like this so that the 2 hydrogens are off the equator, right? Off center, which is going to establish a polarity on this molecule. And that's why this is called a polar molecule. It is polar because at one end of the molecule, there will be the 2 hydrogen charges over here, charges, electrical magnetic charges. And on the opposite end is going to be a negative charge. It's just a simple polarity. Think of a magnet when we were kids and we used to play with magnets, and you have 2 magnets, and if they are of the same, if you have them on the same charge, and you approach one magnet with the other, what happens to the other magnet? Pushes away, and you don't get them to meet, right? But if you flip it so that you have positive to negative, then you get close and boom, they finish and they close up together, right? All right, so that's just polarity. We're not going to get into the theory of electromagnetism, but it's a polarity. So that the positive charge is toward one end of the molecule and the negative charge is toward the other end of the molecule. I also want you to think of this as a three-dimensional model. These are spheres, so you can flip it around whichever way you want. You can flip this around and put the positive on the top and the negative on the bottom. It's still the same molecule, right? Or you can put them to one side or the other. In fact, this molecule is, in 3 dimensions, is twirling around, but it's going to be conserved. In other words, internally, this structure internally is conserved no matter how you twist it around. We can picture that in our minds, all right? But again, water molecules do not exist here on Earth individually. In space, they may be individually floating around, but on Earth, they're definitely linked to one another. And precisely because there are gazillion molecules of water. Imagine how many water molecules are on Earth. It's a finite number, but it's a huge number. It's an absolutely astronomical number. At any rate, these molecules are going to be interacting with each other because of the polarity. And that's going to determine a particular type of interaction, so that the hydrogens of one molecule will be attracted to the bald spot, if you will, of another water molecule, which would be the negative charge. Follow? And so there's going to be a natural attraction to these two ends and a natural repulsion between hydrogens of different molecules, and also a natural repulsion of bald spots of different molecules. Follow? And so this is going to determine a particular pattern of interaction. So there's going to be a preference for the hydrogen ends, either hydrogen end of one molecule to feel attracted to the bald spot of another molecule. And you can continue this ad nauseam with all the trillions and gazillions of water molecules that are interacting with each other. Then, what's the next thing we need to add to this? As we're trying to make this, theoretical model, if you will, or a conceptual model into real life, how it is actually happening on nature. The next factor which we need to add to this, here we're only concentrating on an electrochemical or a electromagnetic interaction, magnetic. But there's another factor we need to add, right? Because anywhere we are in the universe, there's always going to be a particular temperature. And so that will then determine how close or not close these molecules will in fact come together, all right? Because with more heat, and this is general gas laws, remember the gas laws from high school, all right? When we heat up a gas, that gas tends to expand, right? In fact, convection currents, remember? It happens not only with gas, it happens with liquids and even with solids. But it's more drastic on gases because gases don't hold their own volume in contrast to solids. Solids hold their own volume, but gases fill the volume of the container. So do liquids at the bottom part, okay? And so gases, the more they're heated, the more they expand. And that's why if you have a closed container and you heat it up, the gas, what's the normal gas inside just a container would be maybe air. That air, as we saw, is a composition of different gases, right? Mostly nitrogen. Those gases are going to expand until that container may explode. Mm-hmm. Conversely, if we cool down that container and the walls are rigid, then the gas inside is going to actually compress. If you cool it down enough, it's going to change state into from gas to liquid. And if we continue to cool it, eventually to solid. And we do that naturally, or the machine does it for us every day in the kitchen, in the ice box in the freezer, right? So we put liquid into the freezer and it freezes it because the cooling effect is bringing the molecules together, literally. All right. So temperature is crucial, and we cannot get away from temperature anywhere in the universe. So that's the other big factor that is going to determine then and establish what kind of distance these molecules will have, and also how dynamic, how fast or slowly they're interacting and kind of sliding on top of each other. Okay, because at the same time that they're compressed, they're also going to slow down. Okay, John.
There used to be like a delivery company that would bring a big chunk of ice and put that in the ice box.
And that's why it's called the ice box. And some of us from last century still remember the ice box. Exactly right. Yeah. I knew a fellow who loved fishing. He was a jockey. He was an Irish jockey, little guy. And he would come down from the north. He lived up north, and this was at a parish where I was at in the 1980s. And he would come down and he would tell us a story. Of course, he would be coming down since the 50s to Miami when this was rural. So he would get with his wife, they would buy a big chunk of ice on the way down US 1 down to the Keys. There was an ice, Polar Ice or something factory, and they would make ice. So he would buy a big chunk of ice, literally big like this, go down to the Keys, rent a canoe, put the ice chunk in the middle of the canoe, and he would sit on one end, the wife would sit on the other end, and they'd go out for 2 or 3 days fishing, and they would eat the fish and keep the fish in the ice, in the middle of the ice chunk there. Yeah, he loved nature, and the wife put up with it as long as he made money in the races. But yes, the ice cube was it. Yeah, so that was the size of the chunk, huh? And that was the ice box. Yeah, yeah.
But they charge you. Right. They leave the ice factory.
Yeah.
50. And you bring in your milk from them. Yeah. So when they bring it to your house, it's in 70 US 50. The last guy on the stop, you might be only getting 40.
Oh yeah, because it's melting in the meantime, right? It's melting. Yeah. Okay, so very interesting properties about water. This makes water a very interesting molecule. The fact that it's a polar water, a polar molecule, and that's why it's called the almost universal solvent, because most other substances dissolve in water precisely because of its polarity, okay? And so water has very unique qualities, and in the liquid state, even more so, that really enhance the whole possibility for, at the end of the day, for organic life, which again, if we take it down to the biochemical level, it's a soup with a bunch of chemical reactions occurring. Now, let's look at, let's look at the states of water, solid, liquid, and gas. And this is just representation of the distance between the molecules. The range, as I said, in the centigrade scale, Celsius, is established by the change in state from solid to liquid and from liquid to gas. So those states are, they have names, right? This is evaporating, and this is condensing or freezing. Then there is a Fahrenheit scale, which is not based, Mr. Fahrenheit did not base it on the properties of water. I forget one other element or why the scale is off like this, but it doesn't really match a decimal system, okay? The interesting thing about and important about the centigrade scale precisely is that it's decimal from 0 to 100, and that's the standard that is used in science throughout the world because it's homogeneous and universal. It's not tied to a particular country, Great Britain, the UK, which is what invented the Fahrenheit scale.
They use it there.
Fahrenheit?
Britain uses Fahrenheit.
Oh, absolutely. Yeah. Unless you're in the scientific world.
Right.
But for the common folk, just like we do, we use mostly Fahrenheit, right?
Out of France.
Right, because France is already, all of continental Europe is influenced by the decimal system. Okay. And in part, it has to do with Latin also. Okay. The Latin countries, the decimal system is a standard in metrics, not only for temperature, but also for length, for volume, weight, kilos versus pounds, and so forth. Back to the molecule. There's another characteristic about water when it freezes that actually expands, okay? And so let's look at this in a little more detail. There's another one around here. Yeah, this one here. Let me go to this for a moment and stick to this structure of water. In the gas state, we understand that there's no direct association between the molecules because there is enough heat that has been supplied to counteract the attraction between the molecules. Okay, so there's an attraction, there's a magnetic attraction, okay? But that attraction can be overwritten, if you will, to override that attraction with heat. You follow? So that if you supply enough heat to just about any molecule, that molecule starts associating, because what's keeping it associated is these electromagnetic forces. Okay. But you can add a different force that will supply and substitute that, attractive force of magnetism, and that's heat. So in the gaseous state, the water molecules are bounced around against each other and against the walls of the container, whatever that container is, and essentially not bonding. To maintain the atmosphere, though, I want to point out that these water molecules in the gas state still are attracted to what? To an overarching force that influences all of matter, all material on Earth. And what is that force? Hint, starts at the core of the Earth, starts with the inner core. Gravity, exactly. This other je ne sais quoi, like the French say, that pulls things in, all right? That overarching force of attraction. And because, so the water molecules, do they have mass? Do we have mass? Right. Get on the scale, you'll find out what mass you have. Now you multiply that times the gravitational pull, and that's your actual weight, which is measured in newtons, all right? What we call weight, we really have to put it in quotations, because what we're measuring on the scale is really our mass. To get our weight, we would have to multiply our mass in pounds or kilos times the gravitational pull. And that's our real weight, which is measured in newtons, all right, which is the unit for weight. But anyway, these molecules, yes, they have mass. What are the sources, what are the subatomic particles that contribute essentially to the mass of a water molecule? Well, I gave you the hint, they're subatomic particles. So you have three options. What are the three standard subatomic particles? No, I know it's Saturday morning. Protons, neutrons, electrons, right? Protons, neutrons, electrons, subatomic particles make up atoms. Of those three, which are the ones that have a significant or substantial mass? Right, they form the nucleus. The electrons, we call it negligible mass, all right? It's mostly energy then. But protons and neutrons, and that's why they form the core, what we call the nucleus. They have mass. That's the atomic table over there, the periodic table of elements. So the number of protons and neutrons will make a distinction between the different elements and also make them lighter or heavier, right? So because these water molecules, even though they're in gaseous state, they're bouncing around all over the place, they still have mass. And so are they influenced by gravity? Yes or no? Yeah, anything with mass within a gravitational field, all right? And thanks be to that, because if they did not react to gravity, what would happen? They'll float out into space, okay? There's nothing to hold them because the container, so really the container, if you will, in quotations, is gravity. For the atmosphere, the container is gravity, and therefore the atmosphere. The lowest that the atmosphere can go is the surface of the Earth, right here, whatever the surface is, either land or water. Then there's also going to be a dynamic interaction, especially in water, in the oceans, at the surface of the ocean, back and forth, all right? So I want to concentrate on the change in state from liquid to solid, which we know happens at what temperature centigrade? 0. Fahrenheit, 32, okay? Look what happens at the change of state, right? From liquid, look at how the water molecules here are distributed in the liquid. Can you see that these molecules are more bunched up together than these molecules? Yes? For example, 1, 2, 3, 4, 5, 6. I'm just counting the oxygens. 1, 2, 3, 4, 5, 6. How many molecules of water are here in the liquid state? 6. And in the solid state, also 6. All right, so it's the same number of molecules, but where are they more dense? In the liquid state. In the solid state, they are spread out a little bit more because the solid state is also known as a crystalline structure. That's what we call a crystal, right? A crystal formation means that there's an even distance, there's a homogeneous distribution of each molecule or each atom. You can have an atomic crystal or you can have a molecular crystal. Ice is a molecular crystal of water. And you notice that the crystalline structure, the molecules are more evenly distributed to form these hexagons, if you will, all right, this 6-ring shapes. And that's what gives rise to the crystal pattern of snowflakes, that they are a crystal pattern. They have different patterns because of the imperfections within them, all right? But they're always the crystalline pattern. And guess what? Typically they are 1, 2, 3, 4, 5, 6, 6, 6, 6. They mostly replicate the innermost seed core of this 6-molecule structure, all right? Whereas in a liquid form, because of the actual heat that is provided, these molecules are able to bunch up even closer, all right? That's a particular property of water, and it has big, drastic consequences in nature, especially on the lithosphere, on the crust of the Earth. Because precisely on the crust of the Earth, in certain parts of the world, water goes from liquid to solid between what seasons? Between the fall and the winter. Typically there's rain in the summer and in the fall, and then that rain will freeze in the winter, and that has a drastic effect of erosion on the lithosphere, on the rock, okay, which is otherwise hard to break. So let me continue along that argument, and then I'll go back to the specific heat of water, which is another quality it has. You notice then at the macroscopic level, in the fall there will be rain. In the winter, that rain will turn into snow, but even the water that stays around in the cracks. Another property of water is that because it is this magnetic, this molecular magnet, it also tends to stick, right? It tends to stick. It makes, water is sticky because of the magnetism that it has. And so it sticks around, that's what forms capillarity in the cracks of rocks. Then when that water, which got in there in the fall as rain, liquid, come winter, that water freezes, the ice expands and crack. it cracks the rock. And look at this. This is an actual photograph. This is a reconstruction showing the effect of that ice. All right, you can see here 1, 2, 3 cracks, and the third crack was definite. We can expect these other 2 cracks eventually to give way fully, and this boulder then little by little is being fragmented every season over the years, year after year. So little by little, water, just by changing from liquid to solid, is pulverizing the face of the earth. But only in the temperate and polar regions where this happens, when there is thawing and freezing of water, okay? In the equatorial region, there's no freezing. In the polar region, there's no thawing. And so it's the mid-region of the earth, if you will, what we generally call the temperate region, north and south, between equator and poles, that is receiving the most erosion from water, in this sense, in the seasonal temperature change. All right? There's another type of erosion of liquid water simply by running through, which is that friction and dissolving of the material as it runs through. Not only the friction, it's a double action, if you will, the friction, which is a physical action, and then the dissolving of the earth or the soil as it runs through, which is a chemical action, right? And the net effect of the combination of those two, the physical erosion of water and the chemical dissolving of the water of rivers running through an area, cause massive erosion on the earth, massive erosion on the earth. And here are some examples. The Grand Canyon, for example, all right? You can see all the layers over hundreds of thousands, maybe millions of years. That original river was way up here. This is the surface, all right? So this is below sea level. This is below. So these are mountains from the top down. It's like inverted mountains, if you will, yeah. And this is, I don't know, it's 1 mile or something down into the Grand Canyon. And it gets very cold down there, actually. It's hot as Hades up here because it's a desert. You need to take sweaters, I've heard. You need to take sweaters and jackets and stuff because as you go down, it's getting colder and colder and colder. And it's very cold down here during the day. And you need to take jacket with you. Anyway, that's one type of erosion. All these rivers, most rivers, essentially land into or empty out into either lakes or mostly the ocean, right? Vast majority of rivers end up in the ocean. And then at the desembocadura, at the emptying of the river onto the ocean, that's called the delta, all right? And that brings a lot of sediment with it. I can tell you anecdotes. For example, the original port of Rome was Ostia. There's an Ostia Antica, and today there's the new town of Ostia, which means mouth, os in Latin. That's the port of the city of Rome, which is inland, Rome itself. And the river that runs through Rome is the Tiber River. Most important cities in Europe, or large cities in Europe, have a river that goes through it because that was the original source of water for the population. At any rate, from Rome on down to the Mediterranean is basically sea level, so it's navigable. That means that the ships, back in ancient times, the ships from the Mediterranean could come up the Tiber River to the place of Rome, where there was a marketplace for trading. Beyond, if you go up from the Tiber, further up, there are rapids, so it's not navigable as much, okay? So the ships stop there. At any rate, it's brought a lot of sediment over the eons from the peninsula itself. You know, Italy is a peninsula of the Apennines, which is a subsection of the Alps, going east. And so the sediment has been so intense over the millennia with the Tiber that in about 2,000 years since the Roman Empire, Ostia Antica, right, the old city of Ostia, is now inland. It's maybe about a mile away from the shore where the new city of Ostia. So 1 mile sediment from just one river in 2,000 years. Okay, it's amazing. the rivers, how they expand the littoral, they expand the littoral, the coastline, by emptying sediment year after year after year in layers. And if they're seasonal rivers, meaning that they're low in the wintertime because the water is taken up in snow and ice, and then they melt in the summer and so forth, these are seasonal rivers, right? And they deposit also by layers on the shore. And you can see the layers year by year of the type of stone, small, large, etc. Very interesting, the dynamics of rivers and the lifetime of rivers, the sedimentation, erosion. Another type of erosion is by glaciers, which is solid ice, but still a river of ice, which may be 1 or 2 miles thick of height, deep, of solid ice. Imagine the compression, the pressure of that ice. And as it moves slowly but surely, expanding and receding seasonally, is grinding on the bottom. That grinding has been so intense. Consider the Great Lakes of the US, the 5 Great Lakes of the US between Canada and the US. It's estimated that those 5 Great Lakes were carved out by glaciers, expanding and receding. And those are some of the deepest lakes in the world. Very like, which one is it? Not Superior, but the other one where Chicago is. That Lake Michigan, right? It's like a V shape like this, right? Very deep. And that was carved out literally by glaciers on the rock, on the bare rock of the crust of the earth. So they're very slow moving, but significant. They have shaped the surface of the earth, especially the landmass in the northern hemisphere, which is most of the landmass, right? Glaciers. Now I need to go back. No, let me see how far back. Okay, let's go one more, since we are talking about the erosion, just to show you how rivers are also in a dynamic state. We look out the window and we see things pretty much kind of static. Maybe we see, okay, day and night may have a change, but the scale is geologic time, right? And geologic time typically is measured either in thousands, hundreds of thousands of millions of years. So we don't get to watch it just by looking out the window, all right? However, it's real and it's happening, and we are like the beneficiaries of it. And we're just like a little speck in this time frame, time-space dynamic that we call Earth and the surface of the Earth. But this is the evolution of a river. As you see, when it's young, it's pretty straight. And here's a cross-section of how that surface looks. And as that river is moving through, flowing, what is that river doing to the banks of the river, meaning the sides? It is eroding physically by friction, by erosion itself, by carrying, scraping the sides, literally, and chemically by dissolving the sides chemically. Remember the universal solvent? So soil, part of the soil will dissolve into the water. That's what makes it brownish. The other part, well, it doesn't get dissolved in the water, is going to sediment down, right? But because the river is moving, part of that sediment is also scraping. So it's like having a liquid sandpaper moving through the sides, the banks of the river, also scraping the sides, all the material that is moving through the river. All right, it's understood that a young river has more flow, more volume to it. And so it's gradually scraping on the sides. As it scrapes out the side, it's going to hit some areas that are a little more resistant. So no problem, what's the water going to do when it hits an area that's a little higher density, rock or soil? It's just going to move aside, all right, until it gets less resistant, and then it's going to continue its course. What is the understanding here? If this river is, let's assume that it's moving from north to south, or from up to down, actually. What is the force moving this river? Exactly. And so what is not shown, if we were to show the third angle here, we would show an inclination, right? There's an elevation. there's an elevation, there's an altitude component, so that this would be the higher plane and this would be the lower plane, you see? And because there is a gradient, there's an inclination, then the river is going to flow. If there is no inclination, what do you have? No river, you have a lake as the water accumulates because there's no inclination or there's a basin. But if there is an inclination, then the water is going to flow because it's been attracted by the gravity. So you see that it continues to eat away at the sides until it actually forms little islands and inlets like this, okay, and cut off. Yes, St. John's, right, we're at the old age. So we're getting spread out, and the pieces start falling off eventually, little by little, right? Okay, and even as these connect, these areas connect over here, for example, it would generate an island. You think about it organically, and you put this in a bigger scale, it could be that there were a number of animals here. You know, there was a population of animals here, another population. Maybe originally this was a single population of mice that lived in this region. Then they got split by a river. So now you got population A over here, population B, same species of mice, but now they're divided by natural boundary. As these populations stick in the area because they have sufficient grain in each side, here's population A, here's population B, they actually become fully isolated, all right? And mice don't like to swim that much, so they pretty much stick to each other. Originally, they were the same species, but two populations. In a general region, they have the same climate and so forth, the same weather, but now they're geographically isolated into two islands. Eventually, speciation may occur, so that later, when this river is rejuvenated, all right, and maybe these two islands reconnect because of new deposition of sediment, these two populations may not recognize each other. And even though they may look alike to us, to the eye, at the biochemical level, maybe some things have changed, that they don't smell the same, for example, so they don't attract each other and they will not mate. That is the beginning of the possibility of speciation. Then you add the other factors that we talked about, the four forces of evolution, you know, with random mutations and drift and flow and so forth. You may end up with two different species. First, it would be subspecies, eventually two species of mice, started from an original single population. The main factor, if you will, that contributed to that speciation, in this case, was the river, the dynamics of the river over a long period of time. The river aged and then rejuvenated as it found new soil, maybe a new source of water and so forth. Okay, so these are dynamic states, but they are long-term. The big picture here is the erosion that is caused by water, either solid or liquid, in its natural state on the face of the earth, on the crust. But start connecting dots, you know, from the lithosphere, part of the atmosphere, because another component here that is kind of in the background was going to be the original source of water for land in its natural state. Let me repeat the question. What is going to be the original source of water on land in its natural state? We've been having it for a whole week, guys. Rain. Rain upon rain upon rain, okay? Makes a difference if it rains in the plain, the rain on the plain, or if it rains on the mountains. It's going to go through different erosion factors, all right, or different erosion potentials, but erosion nonetheless. Now, let me go back here for a moment to look at another physical property of water, which is the specific heat. The specific heat capacity, every element and every molecule and every material thing on Earth has a specific heat. In other words, the amount of heat that it is comfortable with, that is capable of absorbing, right, at that particular temperature and pressure, at that particular atmosphere. And every element has that, and every material thing has a heat capacity, and that's called the specific heat capacity. For water, it happens to be on the high side compared to other liquids that are other molecules that are liquid in their natural state. Give me another molecule that is liquid in its natural state.
Mercury.
Okay, that happens to be, yeah, it's a metal, and that's why it's an exception, because most metals in their natural state, they are solid, like a piece of iron, a piece of copper, etc. Okay, well, mercury happens to be liquid in natural state. Fine. It's kind of interesting because it also has a concave, a convex meniscus instead of concave and so forth. The meniscus is the edge. It either bends up or bends down when it hits another surface. Has its own properties. But alcohol, for example, you have a bottle of alcohol in its natural state in the cabinet of your room. Hopefully the bathroom is not freezing. It can be cold, but not freezing. Alcohol is liquid. And even below 0 degrees, alcohol will stay, because it has a different heat capacity. But water has a relatively high heat capacity in its liquid state, all right? And it gives you the definition here of what is to change the heat capacity of a molecule is to raise water 1 degree, 1 gram of water, 1 degree. At any rate, that is the heat capacity, which is a measure of energy, right? Heat is energy. And water has a relatively high heat capacity, that we say, meaning that water tends to maintain its temperature, tends to hold on to its temperature. And therefore, in the winter, water tends to stay warmer than the atmosphere, okay, than the rest of the environment. And in the summer, water tends to stay cooler than the atmosphere. And that's why we can go basically swimming year-round in Miami because of the specific heat capacity of water. That is going to have important effects on plants and animals. It kind of expands their living range because water in its liquid state, it maintains its specific heat. All right. Another quality of water itself. Let's see if I've gone through everything in between here. So I'm skipping around a little bit. Okay. Molecular freezing, thawing, specific heat. Oh yes. Associated to specific heat, then, at the global level, it allows for the temperature patterns of water on Earth. And anticipating another slide further down, the volume, so the surface of the Earth. Let's look at this map here of the Earth. Obviously, the equator is here at the center, right? And also, you notice that this Earth has been exaggeratedly squished from the poles. This is not like the Earth looks like. It's near a sphere shape. But for the purpose of showing all the continents, all the land masses in one single plane, this model has been squished at the poles and also put vertically instead of the natural tilt that the Earth has, okay? But what is true to life here, true to reality, is the distribution of water to land, the percentage distribution. Talking about statistics, the percentage distribution. First of all, two things to notice. The most obvious one, the equator is going to be pretty much at the center of this red line, right, of the red band, will be the warmest area. What can you tell me if we trace a horizontal line there regarding the distribution of land masses? Can you tell me about the distribution of land masses? Yes, the quantity, the amount, right, is going to be bigger, larger in the northern hemisphere. You can see it a little better now. Okay. It's obvious that there's more land mass here than there is here, right? Of course, there's Antarctica down here, but even so, even if we were able to visualize Antarctica here, all right, it's not going to be larger than the landmass. Just Siberia by itself is huge. Then you have to add most of Africa, all of Europe, Southeast Asia, all of North America, including Canada, Alaska, Greenland, okay, and even part of South America. So say most of the amount, I don't know actually offhand what the percentage is, but there's more land mass in the north. Therefore, more water on the south. This is at the surface. I'm talking about the surface. In fact, the relation of land to ocean surface overall for the whole Earth is about 3 to 1, right? There's about 75% surface of oceans and 25% land on the surface. But when we talk about volume, it's even more drastic. You understand the difference between surface and volume, right? So this sphere here has a surface, but it also has a volume. The volume of water in the oceans is in the 90%. So most of the water on Earth is in the oceans, and most of the volume of the crust of the Earth is in the oceans. The temperature then, in part because of the heat capacity, when we add, this is the consequence of the rays of the sun coming in and the angle of incidence, right? The angle of incidence, which some of you still need to review a little bit what actually makes, is the concentration of the number of rays that are coming in from the sun, because the sun is so far away and so much massive than we are. Essentially, the Earth is getting the same amount of rays of sun, the same amount of rays. It's just that at the equator, those rays hit a smaller surface. It's a smaller surface defined by a hypothetical circle. Whereas at the poles, that surface increases because of the angle of the poles. So the same amount of rays get distributed into a larger surface, and therefore they heat less at the poles than they heat at the equator, all right? And that is reflected on this composite caricature of the surface of the Earth superimposed with the temperature of the Earth. The net effect is that there is more heat at the equators, and therefore heating the surface of the ocean of the equator, and that surface of the ocean retaining that heat because of its specific heat capacity, holding on to it, all right? Serving as like a radiator, a natural radiator. When those currents get distributed around, you can actually see this graphically. So the surface, the substratum of this figure, if you will, is a caricature, all right? It's a drawing, if you will, all right? But the bands of heat are real. In other words, these bands are superimposed by a computer graphics of the temperature that is, it gives you the scale here in Fahrenheit and centigrade, all right? And this is done by composite layering of satellite imaging of the heat of the Earth, measuring the heat of the Earth, if you will. A satellite, like think of it as a super sophisticated thermometer that is measuring the surface, the temperature at the surface of the Earth. And then all that information digitalized is sent to Earth, and the computer reconstructs that temperature in little tiny minuscule panels, if you will, of temperature, and the overall is this diagram that you can see here. So as we go to the poles, of course, it's going to get colder. In the South Pole, much colder because of the large size of Antarctica compared to the North Pole. So all this is kind of the big picture, if you will, of the heat capacity retention of water. And then because this water is in a dynamic state of fluidity, how that influences the weather patterns of the Earth, of the land masses, which is going to affect, again, mostly the northern hemisphere because that's where most of the continents are. Now I need to go back a little bit to another property of water. We had skipped earlier, it's around here. Here we go. Okay. Associated with the magnetic pull of the molecules, of the water molecules. Now we're going to look at the other end, from liquid to gas, all right? At the interface between liquid and gas. So of the three states of matter, which are the three states of matter? Quickly. Right, the three states of matter. For water, which is the most dense state? Most dense, most concentrated, most thick? Liquid. Just talk about it for the past hour. The most dense, right? Otherwise, ice would sink, but ice floats. Why does ice float? Because solid water is less dense than liquid water. Liquid water is able to push solid water up, called ice, right? Because ice is in a crystalline structure, and the crystalline structure is more expanded. It's less dense, slightly less dense than liquid water, but significant. That slight is significant. The fact that it's slight doesn't mean that it's insignificant. It's very significant, because when you put water molecules together, you have a huge amount of molecules coming together, all right? So bottom line is that liquid water is the most dense of the three states of water. At the surface, when that water changes state from liquid to gas, and where does it do that? At the surface. For example, the ocean, the lake, the surface of this water here, this water bottle, okay, there's a surface. Okay, there is also a dynamic exchange of molecules at the surface. There's a dynamic exchange of molecules, so that some of the molecules in the liquid state are able to exit and dislodge, if you will, from the other liquid molecules into a gaseous state, all right? This is because, what do you think is influencing this dynamic state here of exchange of molecules? The micro temperature. The micro temperature is occurring here. The micro temperature, what is one factor that can make matter change from state to state? Temperature, right? If we add temperature, take water and boil it, you're adding temperature, right? You're adding heat. So here, there's going to be micro heat, if you will, at this level. And that micro heat may be enough for this molecule to be liberated, to compensate and release, let go of the magnetic pull of its neighboring molecules, and will then be released into a gaseous state on the surface and be freed up and start bouncing around, all right, with other molecules, but in a gaseous, more free state. Likewise, some of these molecules, when they get close enough and maybe they have cooled down, all right, they get trapped because the micro heat between these molecules and these molecules may be different. I'm talking about down to the molecular level, because there's heat all over the place. And you don't expect it. It's homogeneous for us in this middle world. Remember the middle world that we live in? Okay, it's an approximation. But when you get down to the very tiny, there's a very dynamic interaction going on there that is, we can imagine it with the mind, with the eye of our mind, and it can be measured with very precise instrumentation, but we can't see it with the eye because we don't have that scale of sight. Remember, we're restricted to the middle one. I'm calling the middle world, that is our external senses. They have a range, but they have a limit to those ranges, to that range. At any rate, there may be these molecules may be just cold enough to attract this molecule in. And now this molecule is going to be interacting with the magnets around it and gets trapped into the liquid. All right, so this is known as the surface tension. There's a surface tension here, whereas to break away, there has to be slightly more heat here than there is in the rest of the volume of the water, right? It requires a little more heat to break away from the surface tension. I'm going to give you another example that is totally the opposite. If I have two containers, one equal volume of water, that's liquid water, and alcohol. Two containers with the same volume, one with pure water, one with pure alcohol. Which one, and if I leave it here at the natural state, over time, what do you think is going to happen to that water? Little by little, it will evaporate. Okay, so it's going to be absorbing heat from the atmosphere and using that heat to release here to break away from the surface tension. But which one, what is your intuition, which will evaporate faster? Water or alcohol? Yeah, think about it. When you rub water between your hands and rub alcohol between your hands, which one evaporates faster? What are you doing by rubbing your hands? You're adding heat. You're adding heat. You're making a transfer of energy, okay? And so alcohol evaporates faster. That's because the surface tension of alcohol is lower, much lower than the surface tension of water. It has to do in part with the heat capacity, with the specific heat capacity, okay? The bottom line, we're getting into much detail of the physical properties here. The surface tension of water is fairly high. Let me just finish this, okay? So that, for example, water tends to stick to itself in the liquid state. And here are several examples. Here is an insect. You know what this insect is called? I don't know the scientific name, but colloquially it's called the water strider, all right? You can see that it's literally sitting or standing on top of water, of liquid water. And it's actually even bending the surface of the water. You can see it very bright. This is a photograph. This is not a, a drawing. This is a photograph of a water strider, several different species, of the surface tension holding up this animal without going through. You can also do this experiment at home with, you can take a paper clip, which has significant weight. Take a paper clip and gently with another paper clip, you can take one paper clip and bend it so that it's like a little fork, all right? And then take another paper clip as it is. And fill a glass with water and lower that paper clip to the surface. I should have brought that. Lower it to the surface. And if the glass is still and there's no motion, that paper clip will stay at the surface of the water, all right? Because of surface tension. It requires a certain amount of energy to break through that tension, either down or up. And the water strider, what we don't see here with the naked eye, is that at the microscopic level, these legs, these 6 legs, have little tiny hair, they're called CT, all right? And these little tiny hairs, microscopic, it's full of them. It could have thousands, maybe, I don't know if it's millions, but probably thousands of little tiny hairs in each one of these legs that vastly expand the surface of the leg. Similar to the convolutions of a brain, if we took out a brain, it would cover, I don't know, a huge amount of area, okay? Because of the folding in and out. It has the same net effect. It is increasing its surface, and therefore it doesn't break the surface tension. There's more surface there, okay? And it's distributing its weight, its little tiny weight, throughout the surface because of those hairs. Equivalent to that is, you know, the gecko, it's not an insurance advertisement, but the gecko that climbs on walls. Why they're able to climb on the wall and then on the ceiling and be against gravity is because, again, at the microscopic level, each one of those pads, the finger pads, is full of these little hairs, little tiny setae, they're called setae, and those hairs increase immensely the surface of the pads of each finger and allows it to grip. Actually, it's a magnet, it's like a little tiny magnet. It's getting magnetized to the wall, all right? And in fact, those setae are highly inefficient because they match the contour of the microsurface of whatever surface it is. But they're very inefficient. If they were more efficient, that gecko would be stuck to the wall and couldn't move. Couldn't move, all right? Because the magnet, the forces are too strong for the legs to fall off. So it's really inefficient, but efficient enough to be able to go against gravity. Very interesting at the molecular level, the forces that are in action that we cannot tell just from plain sight. But we have instruments that are sophisticated enough to measure that. Anyway, surface tension is what makes water bead, like a little bead you see here, right? Why is this water not splashed on that surface flat? Because of its surface tension maintains the integrity of this volume of water. It beats up when it rolls down surfaces. It beats up with swimmers as the swimmer is breaking the surface, but before the swimmer breaks the surface, look at how much this swimmer has managed, you know, the dynamics, the fluid dynamics of this swimmer, how she has managed to crest up the surface of the water because of the speed that she has underneath, right? And the fact that she's protruding somewhat, but not fully yet. She hasn't broken the surface yet to breathe. In the stroke, it's just before breaking the surface when she finally does that final action to push the nose out through the surface tension of the water, enough to breathe, catch the breath for the next stroke, all right? It's a very, very interesting photograph here. It's very telling about the surface tension, how water tends to hold its surface together. Bottom line, called the surface tension. Other examples of erosion then, in the natural state, drastically, when the shoreline is constantly eroding, the ocean currents are constantly eroding the shore. I remember in the 70s when Miami Beach went all the way, the beach actually went all the way up to the seawall of the buildings down in Miami Beach, all right, along Collins Avenue, the old hotels and the seawall, and the erosion had come all the way up. And then in the 80s, the city of Miami Beach put out some huge rafts out into maybe quarter of a mile out offshore with some pumps and machinery and huge tubes, and they started pumping sand. It literally took months to pump the sand back on shore for whatever distance, 200-300 feet offshore, whatever they pumped there. It was all a coarse sand that they were pulling out from about a quarter of a mile away. You can see that machine was all rusted and it was moving through. You can barely hear it from a distance. It was pulling out all this sand with rocks and shells, and it was a haven for beachcombers. We would spend hours going up and down the beach and gathering all kinds of corals and shells and stuff. That was even large chunks that were coming out from the ocean floor out there, all right, and being pumped onto the shore. Now, about 20, 30 years later, that shoreline has been eroded slowly but surely. I went to the beach the other day around 70th, 80th Street, more or less, of Miami. There's a park up there above what is there, Bal Harbor and that area, right? Just before the bridge going over to North Miami and the inlet there. And you walk along the shoreline and you can see that the shoreline gets higher and higher. It's not that it's getting higher, it's that the ocean has been eroding that area. And there's one area that is almost the height of a human already, that has been eroded away. All that used to be flat out into the ocean, okay? So the currents are slowly but surely constantly eroding the shoreline. And here's a very drastic example of that. Obviously, this house was built on land before it was engulfed by the ocean. Even if it's rocky, no matter, these shores, these waves are pounding on that rock constantly, day and night over eons, and pulverizing this rock little by little, okay? Sedimentation, you can see it here, how it's cut right through that rock, even with formations like the hole. You can see that typically these beaches that are near rock formations and mountain formations are rocky beaches or pebble beaches. Most of the beaches in Europe are pebble beaches, also because there's a lot of river runoff from the mountain ranges in Europe. Here, very drastic. This is more sandy. This is sandstone. This is calcareous rock, sedimentary. You know what this is called? These are the famous White Cliffs of Dover, right? White Cliffs of Dover in Great Britain, that can be seen from the coast of France. Just a little white strip, right? The white Cliffs of Dover across the North Sea, right? Continental Europe, and this is the UK. The famous White Cliffs of Dover. Here's another example, more local. This could be Crandon Park over not Biscayne, yeah, or Matheson Hammock over by South Miami area, right? Beyond Old Cutler Road and that area shoreline. This is mangrove. Mangrove has a particular quality that it can grow in salt water. It thrives in salt water. These are the roots. These are aerial roots that lodge into the sedimentary area. And this area has a lot of detritus and a lot of nutrients. So it's a very rich area for plants. But the mangrove has managed to grow in salt water because it has, at its root level, it has something called an active transport system. At the level of root hairs, microscopic root hairs of the mangrove, you realize that the vast majority of plants, when you put them in salt water, what's going to happen to them? They dry, they die, right? They dehydrate because the salt water literally sucks out water from the plant, sucks out pure water. It has to do with the density of water and the fact that salt water has less water per volume because it has salts, okay, than just pure water. So water will diffuse, that's called osmosis. Water will diffuse passively from a high concentration of water to a lower concentration of water. So between fresh water and salt water, okay, which has more density of water, fresh water or salt water? Fresh water has more density of water because for the same volume, in this one pure fresh water, you have only water. And at the same volume, you have water and salts. So proportionately, there is less water in salt water than in fresh water. And so osmosis, the passive diffusion of water, is going to be from the fresh water to the salt water. And that's what happens to the vast majority of plants. If you water plants with salt water, you're going to dry them out. You're going to kill them because that salt water is going to suck out water, or water from the plant is going to diffuse out into the ocean, okay? Except the mangrove and a few other plants that have managed that to survive because of what is called an active transport system, meaning that at the level of the root hairs, which are microscopic, individual root hairs, actually suck water from the ocean. They suck water from water molecules from the ocean. Of course, they have to invest energy in that, a lot of energy, all right? So it costs the plant energy to do that. But so what? Because since the plant is producing an excess amount of energy. By what process? The plant is producing, that's why they're producers, an excess amount of energy. By photosynthesis, from light energy from the sun into chemical energy in glucose. So the plant has an excess amount of glucose. And a good bit of that amount of glucose then is going to go to the root hairs to provide the energy for those hairs to literally suck up water from the ocean and allow them to live then on the coastline. It's an adaptation. It's a drastic adaptation. It is elegant, and it has allowed the mangrove to conquer the shoreline. And in doing that, the mangrove then stabilizes the shoreline. Because then with these roots, which are very entangled, as you can see, they accumulate detritus and sediment, and they stabilize the coast so that they prevent beach erosion. All right? And when the mangrove is missing, you can see graphically and literally that the shoreline goes in. All right? Because then as mild as that current can be, or even just the tide coming in and out will be sufficient to erode the coastline. You go out to Matheson Hammock, you can see this. Wherever mangrove is missing, the shoreline comes in, all the way up to the road, actually. It's eroding the road already, okay? And so mangrove now has been protected. It used to be cut down for seawall and for developing the shoreline. Now, thanks be to God, finally in the US it's protected. There's very little mangrove. I think Florida is the only part of the only state that has mangrove of the continental states. I don't think California, and by the time you get to Oregon, it's too cold already. So they don't have mangrove. So we're it. Florida is the state that has the mangrove.
It also provides a natural habitat.
It does, to the point that the vast majority of fish, pelagic fish, you know about pelagic already, it is open water fish. I'm talking about sailfin, I'm talking about sharks, large fish that live in the open water, dolphin, fish, you name it, they come to spawn at the mangroves. They lay their eggs here and then they flee out, typically overnight. And so all the baby fish, the vast majority of baby fish are born along these mangrove and these tropical regions. And so they definitely need to be protected. Okay. All right, where we go from here? Since we're talking about freshwater and saltwater, it's important now to look a little bit at the chemical composition, because you understand that this water runoff from rivers throughout eons, plus the water in the oceans itself cycling through the bottom of the ocean, all right, is dissolving, has been constantly dissolving chemicals into the water, mostly salts. Salts have been dissolved into water over millions of years, and that is called the salinity of the water. So that fresh water has very, very little salinity, and ocean water has the most salinity. And not all oceans have the same salinity. Some oceans are more salty than others, okay? And seas, which tend to be oceans that are surrounded by land, small saltwater, relatively small but larger than lakes, those we usually call seas, right? All right, so let's look at the composition, or the chemical composition of water, natural water, in liquid form as the recipient of all these, as a solvent. It's a solvent, in other words, all the chemicals that dissolve into water. Well, the list of chemicals is huge. Even gold and silver and precious metals that are dissolved at the molecular level in water, all right? But in very minute quantity. In fact, over the years, you hear of some upstart company that wants to suck out the gold that is in the oceans, but the machinery is so expensive that it doesn't pay. But there is basically all the elements on Earth practically are dissolved in water or suspended in water in the oceans one way or another. But some are in a much larger quantity than others. The ones that are in most larger quantity typically are salts, because they are the ones that dissolve easier. all right? And salts, as you know, can be divided into anions or cations, depending if they have a negative or a positive charge. This is at the level of the elements. Some elements have a negative charge, some elements have a positive charge. Again, that makes them polar. And when they come together, they form a salt, like sodium chloride. What's another name for sodium chloride? Table salt, right? What we call table salt. It's actually about a dozen different salts dissolved in the ocean. And this is a list of them. I don't expect you to know the percentages or anything like that, just as a simple reference to know the that what makes the ocean salty, basically. All right, well, it's a number of salts, but it's not just sodium chloride. It's a dozen different salts that are dissolved in the ocean, all right? So when we look at the concentration, the chemical composition or the concentration of salts in the ocean, typically the scale is parts per thousand, and that's what this PPT means. PPT is parts per thousand, all right? Parts per thousand. And that's the standard scale for measuring the chemical composition of water in its natural state. So we can go all the way from, let's say, a freshwater lake. Let's say it's a lake that is high altitude, it's a primary lake. What would be a primary lake? What do I mean by primary lake? The primary lake would be typically high on a mountain near a glacier where it gets glacial melt. And so it's getting water that is fairly pure, fresh water, has very little minerals in it, because that water has not had a time to run through the mountain and dissolve soil in a river form, right? So that would be what I'm calling a primary lake. That would be, contrast that water to, let's say, the ocean that has been getting the runoff of rivers and lakes over millions of years. Which one would you expect to have more concentration of minerals? The primary lake or the ocean? More concentration of minerals on the ocean. More salty, the ocean, right? So from that fresh water, globally, fresh water is less than half part per thousand. In fact, the scale that is used here is so small, it's 0.5 part per thousand, or less than half part per thousand, right? So sometimes to measure the salinity or the salt or the mineral concentration of freshwater rivers and freshwater lakes, they use parts per million instead of parts per thousand. So it would be ppm. But this scale in PPT allows us to look at a range all the way down to the ocean level, which is the highest is anywhere between 32 to 37 parts per thousand of mineral concentration, most of which are salts, all right? Anions and cations. So that's the range. Brackish or estuary waters is halfway through, anywhere from 0.5 to 17. Okay, that's the full range. And this depends on the tide also. If the tide is flowing in or out, that's going to change this estuary composition, right? But if the tide is flowing out, it's going to be more fresh water than salt. If the tide is coming in, then it's going to be more salt water than fresh. And so there's a greater fluctuation in estuaries, In general, we can expect it in the Atlantic to fluctuate once a day from low to high salinity. In the Pacific, because it's much larger, has two tides, so twice a day, the dynamics of salinity changing back and forth. So think of the ecosystem, think of the plants and animals that live in estuaries. They're more adaptable to that range. They have to adapt to a larger range, okay? That's aside from the flow up and down of water, where some of these animals are exposed to land, air during low tide, and then exposed to water during high tide and so forth. So typically animals and plants that live in estuaries have a larger range of adaptation. All right, so this is the overall range from half part per thousand in freshwater to an average of 35 part per thousand in the oceans in general. The oceans are communicated through each other, all right? However, different oceans and different parts of the ocean have different salinity, again, when there is more or less evaporation. The other thing to consider also when there is evaporation, let's say at the tropics, is mostly water that is evaporating. So that will leave a higher concentration of salt behind compared to near the poles where there's less evaporation going on and therefore more water for the same amount of salt and therefore less salty generally. If you add to that the melt of ice that is occurring at the edge of the North Pole and the South Pole, that is mostly freshwater ice that is melting into the water. So that's another factor that contributes to the polar oceans being less salty than the equatorial oceans, right? What else? Oh, so look at the sea. I said that generally when we talk about a sea, it is typically salt water surrounded by landmass, the Mediterranean Sea, the Black Sea, the Dead Sea, all right? I wish I had the Dead Sea here because here's the Black Sea, oops. And what happened to the Black Sea? When you compare its salinity, its PPT is 16 compared to the average of the oceans, 35 parts per thousand. What's the ratio here?
Nearly half.
Half, right? Nearly half. So what's happening to the Black Sea? It's becoming less and less salty, more and more fresh. If Black Sea is surrounded, it's a landlocked, right? Russia and Turkey, that's where the Strait of Bosphorus is. It empties out into the Mediterranean through the Bosphorus Strait and is getting filled by fresh water from the mountains that are surrounding the sea. So it's becoming more and more fresh water. Animals that may have been trapped there originally, which were marine animals, right? When the sea levels were higher, and now they either adapt to fresh water or they die. Another example happened drastically in Nicaragua in the two lakes that they have, the Blue Lake and the Green Lake, Lago Azul, Lago Verde. In Nicaragua, those were volcanic lakes, and that whole region of Central America at one time was on the water, right? Was the ocean, because remember the North American plate and the South American plate were two independent plates that gradually pulled away from Europe and Africa and migrated close to each other. And eventually the Isthmus of Panama was formed. The oceans were separated and Central America came literally from the bottom of the ocean up. And so those two craters, as they came up, the waters receded, trapped saltwater fish in them. And some of those saltwater fish were sharks. And as those lakes, little by little, from the tropical rains that were falling, that have been falling in Central America over eons, all right, those lakes have become freshwater lakes, freshwater seas. They're small, so they're called lakes, but they used to be saltwater. The point is that most of those fish died off, but some fish, which are very hardy, manage to survive in freshwater, and those are the famous freshwater sharks in Nicaragua that are in these lakes, Lago Azul, Lago Verde. And every now and then, some of those sharks happen to be some of the more aggressive sharks in the that are in the Pacific Ocean and in the Atlantic also, like the bull shark and the other one I think is the white tip. Anyway, they were originally pelagic sharks, open water sharks that tend to be more aggressive than the coastal sharks, simply because they run out of food, they run into food more seldom, and therefore they're very good hunters. Anyway, combination of factors, these lakes are a little higher than sea level and they drain off. They have rivers, especially during the rainy season. They drain off onto rivers that go through the countryside and eventually empty out into the Pacific. And some of the sharks, sometimes when they're small enough, they get into this lake, into these rivers. And there have been cases reported where farmers have been taking their cattle to the river to drink water, and some of these cattle get attacked by sharks in the river. Okay, and humans have to be careful because they can get attacked by these sharks too, which are freshwater sharks. They have adapted through regulating their the salt content in their body. John?
I walked outside for a second.
Yep.
Did you mention a little organ that changed in them? I learned that at University of Miami.
Is it?
That population of sharks has a little organ
Okay.
that helps filter out salt. And it became vestigial. It lost its function.
Interesting.
Yeah, that's what they were talking
Ah,
about.
very interesting. I didn't know that what was physically responsible. So it's some organ that they have associated with the, I think the gills also do some osmoregulation, all right? And the nephritic tissue, equivalent to our kidneys, would regulate the salt content. But
I think it's in their bull sharks.
they are, right? Yeah, they're very...
That's what maybe they might be able to make it back into the salt.
Right, because they don't have that, that organ has become vestigial, right? So, right, they're locked into living in freshwater.
And this was where you were saying?
In Nicaragua, in Central America. There may be other countries in Central America that have them, but I know for sure in these two lakes known as the Blue Lake and the Green Lake, Nicaragua. Yeah, it's very interesting to look at that. So at any rate, that's a drastic example on the desalinizing, if you will, of salt water. On the opposite end is the Dead Sea in Israel, which is also landlocked, and it happens to be one of the lowest places on Earth. It's actually below sea level, all right, but it's landlocked. The Dead Sea, that's where the Jordan River empties, coming out from the Sea of Galilee. Jordan River flowing pretty much south into the Dead Sea, which has now split into two parts, and the lower part of the Dead Sea is very shallow. It's only about 5 or 6 feet and is disappearing. The concentration of salt is huge. I think, if I remember correctly, it's about 10 times more salty than the average concentration of salt in the ocean. Let's see, Dead Sea salt concentration. Or it was yeah, any one of these.
Wow.
Yeah. Yeah, instead of, so 35 parts per thousand, right, is how many parts per 100. Percentage, biostatistics. The ogre of biostatistics. Okay, 35 parts per thousand is the average salinity for the ocean, right? Off here at Miami Beach, 35 parts per thousand. Translate that, so PPT, parts per thousand. Translate that to parts per 100. So is 3 parts per 100. 3.3 parts per 100, okay? This is 33 parts per 100. So if we would make this in parts per 1,000, move the 0 over, this would be 330 parts per 1,000. So 10 times more salty. Here's a picture, all right, a photograph. More salty than the ocean, than the average ocean, the Dead Sea. And that's why it's called dead, because nothing lives there. Recently, some time ago, they discovered some bacteria that actually live in the Dead Sea. I had the privilege of going to Israel one time and just visiting the Dead Sea. You can float vertically. You walk into the Dead Sea, you can float vertically. You don't have to stand out horizontally. You can float like this. Okay, you bob like a buoy. Mm-hmm. Yeah, if you have a little cut, you'll feel it right away. It feels like a burn, all right? So make sure you have any cuts on your body because you'll feel it. Don't put your head under the water because it will burn your eyes, will burn your mouth, your ears. So you have to stay above, all right? But it's very medicinal also. And the sand, the mud is very fine, and they sell the mud for cosmetics and all that. And it's a big industry They have there on the shore of the Dead Sea spas, health spas that are very famous throughout the world. People go from all over the world to get their treatments there. But yeah, what you see here floating, they look like little icebergs, right? But they're not icebergs. You know what this is? These are salt cakes. So it's so salty that the salt naturally clusters and crystallizes, all right? And then it floats around. So you look at the horizon, you see these cakes, these little, it looks like little tiny icebergs.
You know what? You look like Father like, I'm not going to drink beer, but you know that thing on top of the beer? Froth.
The froth and the foam.
Yeah, it's foam, froth.
It can look a little bit like that, yeah.
Those are solid though, right?
But this is solid, yeah. This is solid crystals. These are crystals. So it's not so much foam. Aside, it also foams on the shore, all right? But these are actually crystals, globs of salt that are floating because it's so salty that the salt naturally comes out. Yeah, so it's called hypersaline solution. And the plants, the bacteria that live here precisely, we talked about them, are halophiles, right? They love salt. They live in high salt concentration. These are extremophiles. Remember I talked about the bacteria that are extremophiles? Some like high temperature, for example, geysers from like in Yellowstone. Some are halophiles. They love salt, all right? High salt concentration. Yeah, these archaebacteria or archaea, and but also bacteria, and they're called extremophiles. They love extreme conditions, some high salt, some high temperature, some pressure, some no oxygen, all right? They're called extremophiles, and while I'm on that line, when some of these bacteria and archaea actually can tolerate several of these conditions together, high salt, high temperature, no oxygen, anaerobic conditions, those are called polyextremophiles. And there are a few bacteria that have been identified as polyextremophiles. And the potential with those bacteria is that you can take them to a place that has no atmosphere, high salt concentration, very little water, high pressure, high temperature, like for example, the surface of Mars, and release them and possibly start growing. And that would be a process that is known as terraforming Mars. It's a wild project, but it's beginning to happen already. There are plans for it. Who knows how long this will take? The scale for Earth was in the millions of years, but to essentially seed another planet with these polyextremophiles. Remember, most of the oxygen on Earth came from cyanobacteria, you know, which were extremophiles when they started because there was essentially no oxygen, and but there was a huge amount of CO2 compared to today. They used that for beginning to photosynthesize and produce oxygen as a byproduct, and that's essentially the oxygen that we have today in the atmosphere. All right, 20% of the air in front of us. So these extremophiles have an incredible potential. They're also used in the lab under extreme conditions and so forth. Some of it, I'm sure, is classified. It has military implications. It has commercial implications and so forth. And it also has ethical implications, right? Because we can ask the question, do we have a right to terraform another planet? Who knows what's going to come of that planet, all right, as it evolves with life. Interesting. Okay, back to our humble little planet Earth and water. We got the salinity then. You understand what salinity is? So if I ask you, we go on a field trip to Miami Beach one day and we're looking at the Atlantic Ocean. Okay, what's the salinity of this water? 35 ppt. All right. And it's about a dozen different minerals dissolved in there. Currents. Look at the currents. These are the patterns at the global level. These are the currents, which is, again, the Coriolis effect, the spinning of the Earth. This is at the surface. There are surface currents. There are deep ocean currents going on, all right? But this is the general pattern, mostly of the surface currents of the ocean. As you can see, it's a twirling effect. Look at the Atlantic, North Atlantic, South Atlantic is going to be in the opposite direction. The Indian Current, actually in the south, is going to be counterclockwise. The surface of the ocean, different from the pattern on the atmosphere, right, which is in the opposite direction. The Pacific, South Pacific, is counterclockwise. North Pacific clockwise. Half of it here, the other half shown here. And that's why in the Atlantic, in the North Atlantic, what's the current that is very prevalent for us off the coast? Again, we're standing at Miami Beach and looking out. The Gulf Stream. Gulf Stream. Are we going fishing in the Gulf Stream? No, there's a racetrack that was named after it. The Gulf Stream racetrack way back. All right. So the Gulf Stream is this current. It starts as an equatorial current, gets into the Caribbean, gets kind of trapped into the Gulf of Mexico, heats up in the Gulf of Mexico, fairly shallow, and then the only way out is through the Straits of Florida, between Florida and Cuba, right? 90 miles there. And then it heads up, is being pushed up against the shoreline, up through Miami, Florida, and then the Georgia, the Carolinas, at the easternmost point there in the Carolinas, Cape Hatteras, right? Cape Hatteras pushes it offshore and eventually ends up in Ireland. There's Ireland, okay? And then Great Britain over here. And that's why it pumps relatively warmer air and water onto Ireland. And that's why Ireland, seldom there is snow, but there's a lot of rain because of the warm, humid air that this Gulf Stream is bringing, that then becomes a North Atlantic current, meeting the cold air up here, condensing and precipitating. Cools off, comes down the coast of Iberian Peninsula and Northern Africa, picking up heat again and continuing the cycle. Just following one example in detail, but in the big picture, then we have these gyres. They're called gyres, G-Y-R-E, and there are 5 big gyres, all right? 5 big gyres that correspond to the 5 big oceans of the world. Starting with the North Atlantic, simply because we were here, the North Atlantic gyre, you see it, clockwise. It's like a huge whirlpool going around and around over eons, eroding the coastlines and making a spin, if you will, of these currents. The North Atlantic gyre. Cross the equator, and you get the South Atlantic gyre. Moved in between Africa and Australia, you get the Indian Ocean gyre, because here's the India subcontinent, all right? Smaller gyres on the side, but the big one here is the Indian Ocean gyre. Let's come out to the Pacific Ocean through the current that goes around Antarctica, all right? And again, we end up with 2 gyres. If we are in the South Pacific, the South Pacific gyre. Again, counterclockwise, move to the north, and the twist turns in the opposite direction, the North Pacific gyre, clockwise, all right? And that is going to bring down, so it's water that is going along the equator, the northern part of the equator, warm, picking up heat from the angle of incidence, and hits, what does it hit over here? Philippines, Japan, starts going up the coast of Asia. Eventually, here's the Korean Peninsula, Siberia. As it does that, it starts cooling, right? And then it's going to cross the Iberian Straits here, the Siberian Straits, down the coast of Alaska and North America. And this is the famous California Current, which is opposite direction from the Gulf Stream and opposite temperature. Gulf Stream warmer than what we deserve by latitude, and the California Current colder than what they deserve by latitude, all right, because the water is either moving up from the tropics in the Atlantic or down from the polar regions in the Pacific. All right, almost done here. The caps, simply to point out the polar caps, that there is solid water held up in these two caps, whether it's Antarctica or the North Pole. Antarctica being a continent, so there's a solid landmass underneath this ice cap. Whereas in the North Pole, for many years and centuries, it was assumed that there was landmass underneath the North Pole, but not really known, all right, whether there was a landmass or not. I mean, it stands to reason, right? The intuition is that the ice is on top of a landmass, otherwise why sit there? Why this ice would sit there? Now, Greenland is a landmass. Greenland is an island, Groenland, but the one that proved definitively that the North Pole is not a continent, but it's essentially a huge ice cube sitting on top of the North Atlantic Ocean, all right, is a submarine. Now, why did we have to wait until the submarine? This is the first nuclear submarine, nuclear power submarine, nuclear power. Why did it have to be nuclear power?
It couldn't surface to recharge the batteries.
Exactly. So it cannot be a diesel. The previous generation of subs, right, was run essentially by piston engine or maybe electric. But the point is that they did not have enough fuel. The submarines did not have enough fuel to go underneath the North Pole from edge to edge, all right? Which I don't know how long it takes actually, but the Nautilus was the first one in 1958 and proved convincingly that there was no continent on there because it went underneath from one edge of the pole to the other, of the North Pole, and did not hit into any landmass. Okay, but just a little curiosity. But the North Pole is essentially then a huge ice cube that is sitting on top of the Arctic Circle, on top of the North Atlantic Sea, surrounded, as you can see, by several different continents, right? Eurasia on one side and North America on the other side. Finalizing then, coming to the final stretch here, we have glacier coming down and eroding and melting at the edge. Solid water, I already explained the erosion. Look at the drastic erosion here. Nothing is growing at the microscopic level, certainly not next to the glacier, because this glacier will also evolve seasonally, thick and thin, right? But I can see some greenery over here at the edge, which is probably that delimits the height of this glacier as it grows seasonally in the wintertime, and then it thaws gradually into the summertime and back and forth. But they would have a cycle emptying into the first, those primary lakes. They're called cirques. Cirque Lake, or Cirque, is the primary lake receiving water from a glacier. Eventually, those lakes empty out into rivers, which is already liquid water, right? All right, here we see a drastic example of a glacier receding and melting away, attributed to climate change. Now, the big question is this man-made? Is this an effect of human action or not? Okay, that's the big question, because this is evident. It is obviously, this glacier is obviously disappearing and receding. I mean, originally, it would cover all this area where we see the erosion happening, right? This erosion on the scale here, I mean, this is a huge scale. These are mountain ranges, probably Alaska. So all this recession has left this basin barren. And in fact, over the past 500,000 years, 500,000 years, all right? 500,000 years, which is really small in the time scale. We have evidence of 4 glacial periods. There have been 4 melting, 4 interglacial, 1, because the scale thawing out. 1, 2, 3, 4. The 5th one, all right, the most recent one. Here we are today, and this is just 500,000 years. There's been this cycling, broadly, cycling into 4 glacial periods and 5 interglacial periods. So technically we are now into an interglacial period, but we're not fully interglacial. It could go higher. There's evidence where it's gone higher, up to 40 degrees centigrade. 40 degrees is hot. You know, it's like in the 90s for Fahrenheit. This is what we call the tropical Earth. The Earth at this stage was tropicalized, where the poles were practically melted, all right? And there was forest, tropical rainforest growing, let's say in Alaska, which today is a coniferous forest. What's the evidence for that? Well, the oil, the petroleum that is down there, which is estimated to be rotten tropical rainforest. So that was when the Earth was tropicalized. At the opposite end, in the glacial periods, where the glacials receded, came down practically to the southern part of the United States, there's evidence of glaciers, except perhaps the peninsula of Florida, just a little edge along the southern border of the United States. Then we say that the Earth was winterized during those times, okay? Those were the glacial periods. So what I want to point out here again in kind of the big picture is this oscillation. With a little imagination, you can see kind of a sinusoid wave going up and down 4 times and up 5 times. And that would be considered as cycles. But they're big in scale. And even this is as far as we've been able to measure, who knows, beyond the 500,000 years, which is relatively recent, right? Because the Earth itself has been around for 4.5 billion years. So a billion is 1,000 million, right? So there could be thousands of these cycles back into the early history of the Earth. Well, we couldn't get too far because we needed water actually in liquid state. But several billion years, there was water in liquid state already. Question?
How were they able to document this?
Right, mostly by ice cores and then estimating. So the margin of error, again, going back to stats, to biostatistics, the margin of error can be large, these measures, okay? But they do a lot of statistical analysis, a lot of number crunching. And they use mostly cores, ice cores, drilled down in Antarctica. It's a big lab, all right, where the different nations of the world have stations, scientific stations, also in the North Pole and Greenland. As Greenland is melting, it's exposing, and they can go deeper with these ice cores. So it's an approximation, it's an estimation. One of the things they look at in ice cores is the CO2 content, and you'll see different bands on the core, right? It's a long cylinder of ice. It can be long this room or much longer than this room. And then they go section by section, seeing the amount of gases that are trapped in there, okay? And determining the proportion of gases, see how much CO2. Remember, CO2 is less than 1% of the atmosphere, very small amount. But so a little fluctuation in that can be significant and point to a tropicalization or a winterization of the Earth. But it's very approximate, very approximate. So it's really modeling, and every model sooner or later is doomed to fail, right? For a more sophisticated model. Let's look briefly at this little YouTube here, because it's pretty dramatic. Oh, you know, all the time I forgot to put the microphone. Well, this is in case someone out there had a question. You can always call me by phone if anyone has a question listening. Let me see. This is supposed to be a video. Oops. Oh, let me go back. Oh. Apologize that I did not test. I just trusted the link, but now it's not working. Supposed to show the tropicalization and winterization of the North Pole moving in and out. Sorry, folks, let me see. Well, we can always do this. Let's go back. Okay, let me just Google it for a moment. This was areas. Okay, so okay, this one works. Okay. Notice the years down here. Let me start it again. Okay, hold for a moment. All right, see this scale of hundreds of numbers in Ka. What is Ka? It's kilo years, okay? So thousands of years before the present. So it's going to start about 500 somewhere. In other words, 500,000 years ago, right? 500,000, 100,000 of years. Let's go back to the first one. Okay, here we go. So you see this is a model, a computer model, obviously, but the ice, if you want to concentrate on this area, this is the ice receding and expanding. This is North America. Here's Florida, okay, this is Cuba. So the ice receding and expanding back and forth. I don't know if that was the second one or the third one, but see, back and forth, back and forth. Now we're down to 100,000 years ago. I believe the last one was about 10,000 years ago. Look at that recession, right? Winterization and then tropicalization. Back and forth. 50,000 years ago. Now I think the last one coming up, about 10,000 years ago. Now that's the present. Okay. There's another one. I don't want to take time. I'll look it up on my own time and then show it next time. But there was another one of literally a river running through Greenland. All right, a river of melting ice running through Greenland, emptying out into the ocean. It's dramatic. It's really dramatic to see that, and that is a film. That is in real life. But I don't have the link now, so I'll find it next time. I want to wrap it up. Just two more slides here. One is the number, just the volumes. So to put it in perspective, since we've been concentrating on the hydrosphere, the amount of water naturally on Earth in its liquid form, 97% of it is in the oceans. It's in the oceans. That's why I say by surface, it's about 3/4 of the Earth, right? About 75, 78% surface. But volume is practically all of the water, of liquid water on Earth. 97% of it is in the oceans by volume. The 3% that is not in the oceans then is subdivided into mostly glaciers and ice caps, right? And then a second slice, which is smaller but significant, 20% of that, in other words, 20% of the 3%, right, is groundwater. What does it mean by groundwater? It's trapped, essentially trapped underneath us. The aquifer, the groundwater that is underneath the surface, the crust. And that is mostly the source of water for many cities of the world, right? Think about it in the human population side. So that's about 20% of 3%, so very small amount, very small fraction. And the rest is essentially trapped in ice, in glaciers and ice caps, of which are much bigger by far, the poles or glaciers.
Is that 5.2% for the lakes or 52?
52, yeah, hold on, I'm not there yet. I'm still talking about the ice caps and glaciers. You realize that between these two categories, ice caps and glaciers, by far, the ice caps are much bigger than just the glaciers, right? Glaciers would be in the Himalayas, in the Alps, in the Andes, in the, I don't know if there are any glaciers in the Andes, probably very small, in the, over here in the Rockies. But the ice caps, it's a much more substantial amount of ice there. But even that is only 80% of 3%, okay? If it was 75%, you know, or actually if this was 66, it's about 2%. Of this 3%, about 2%, more or less. 2% is in the ice caps, okay? North Pole and South Pole specifically. All right, the remaining, what is left of that, this little fraction here, which is about 1% of a 3%, in other words, 0.3% of the grand total, that is subdivided again into lakes, which is about half, 52% lakes, half. And the other half is subdivided into just moisture in the soil, which is what's accessible for plants specifically, right? Moisture in the soil, living organisms, the water within us, which we're mostly water. All organisms are mostly water, right? 80% more or less water. 90% for the young. Another 1% in rivers, water vapor in the atmosphere, 8%, but very small fraction. And that is essentially the water that we have for life, for maintaining life. So it's a very small fraction of the overall water on Earth that is available for life, okay? Of course, that doesn't include, that is excluding all the organisms that live in the ocean, which are using this 97%, okay, obviously. But they're using it for life, for living in there, but not internally in their organism. One last thing that I want to point about this, and then I'll go to the final slide, is that even if all the ice caps would melt, in other words, if the North Pole and the South Pole would both melt 100% barren, so that the North Pole would disappear because it's an ice cube, and Antarctica would become just a barren continent, right? With no ice. How much percentage of water would be added to the total volume? To the total volume, the absolute maximum water that can be added to the total volume of water on Earth is 3%. Is 3%. Because the other 97% is already liquid in the oceans, right? So even if both poles melted tonight or tomorrow morning, the maximum volume of water that could grow is 3%. But that's volume. That doesn't tell us about the surface. The surface will So that volume will go up 3%. And then it's a question of shallow areas, areas that are the coastline is the one that is most affected because shallow areas, like for example, us, we are an average, what's the average height of South Florida above sea level? I think it's about 6 feet above sea level. It's the average height of South Florida, 6 feet. So that 3% will certainly rise the level of the oceans way above 3 feet. I don't know exactly how much, but above 3 feet. And so we would again become an underwater peninsula, all right? Essentially back to a coral reef, which is, that's why our limestone is fossilized coral, because this used to be a fossilized coral peninsula, right? With several hundred feet of water on top of us, salt water. So even that 3% is enough to eat up into the coastline throughout the whole world, but especially low-lying areas. If you have mountains like in the California area, that's not going to affect it as much because the mountain range is higher. Okay, so we always have to put it in perspective and proportion. One thing is the surface, and another thing is the volume. The volume itself will rise slightly, but the surface, in other words, the low-lying areas, the coastlines, are the ones that would be mostly affected by this sea level rise. Right? Makes sense. All right. Much more urgent than sea level rise is freshwater access to drinking water. This is being called more and more liquid gold, okay, figuratively speaking, because it's becoming more and more scarce throughout the world in different parts of the world. Drinking water, not just water, because one thing is sewer water, right? But who can drink that? And in fact, a large percentage of the population of the world, millions of people in the world don't have access to drinking water. They're drinking sewer water, they're drinking contaminated water, and literally thousands of people, mostly children, are dying every day from contaminated water because they don't have access. These populations don't have access to drinking water. And so all recent popes have spoken about water and the right, the natural right to drinking water. Right? You hold on to this for a minute. If you can share, then I'll give you an extra copy. All of our recent popes, thank God, have spoken about the natural right to water, to drinking water, to potable water. All right. Flip the page for a moment. We can start with Paul VI, who the modern popes from John the 23rd forward, because John the 23rd died prematurely there at the council. All right. He started the Vatican Council in 1962 in the spring, and then in the fall he died, and therefore. But then Paul VI was elected right in the middle of the council and continued it until 1965, right? And in 1975, Paul VI was already making statements about water, and this was in the specific context of a desalination process, desalinizing salt water, right? Desalinizing plants. One time I was in Guantanamo, Cuba, and in the base, the military base of Guantanamo, and the whole military base of Guantanamo is being run, the fresh water, drinking potable water is being run by desalinizing plants from the ocean. So they don't have to depend on the city water coming from communist Cuba, all right? And so these plants are possible. There's high technology, sophisticated talent. They take quite a bit of energy to run, but essentially it's like a humongous kidney, if you will, that filters out the salt to water. Also, the military base in Key West is also run by a desalinizing plant because they become independent from the source of water in the city and so forth for security reasons. But so this was Pope Paul VI here meeting with, back then, Cardinal Motilla, all right? And then it was John Paul II's turn to talk about water. Also, you go up the back side of the page here, kind of backwards. In 2004, at a conference in Brazil on the natural right to water. All right, you can read the statements later at home, please, as a little homework, if you will. And then Benedict XVI, so now we have Benedict XVI at an international exposition on sustainable development, right? In 2008, also a statement on the natural right to water. Finally, Pope Francis, and this is the actual conference here, last year. And this was so providential because, you know, the first cohort of this program was last year, right? They graduated in December of last year, and they started like yourselves in the fall of the previous year. So in the summer of last year, I'm teaching the same course to the previous cohort, the first cohort of this program. And just February, looks like 3 or 4 months prior to this course, last year, Pope Francis was addressing the Pontifical Academy for the Sciences, which was founded way back in the 1950s, I think it was, to more than half a century ago, to advise the Holy Father on scientific matters. The members of the Pontifical Academy for Sciences don't have to be Catholic, they don't have to be Christian, they don't have to be believers in God. They just have to be top-notch scientists. And they're invited to participate in this academy, which is a Pontifical Academy, and they advise the Holy Father on scientific matters. And they're astrophysicists, they're chemists, they're mathematicians, all kinds of economists, you know, there are different fields of science in the world, including the social sciences. And this is the panel here, and he's addressing that Pontifical Academy on the occasion of a conference on the human right to water specifically, all right? And that's the front page, the whole thing there, that's the entire discourse. Take the time to read it, please. This is just last year. I mean, this is kind of fresh off the page, if you will. The natural thing about it, no one would think of selling air, right? Well, actually it became a fashion a little while ago to sell air in canned air. It was a fashion in Europe, and then it spread over here and other places to buy canned air from Paris, for example. Who would want to breathe Parisian air, right? But it's a fact. Really, we breathe naturally, and no one is charging you for the air that we breathe. Well, water is as essential to life daily as the air that we're breathing. In fact, it's also a fluid, all right? It's a thicker fluid, but it's a fluid nonetheless. And we're increasingly paying for water more and more, even in the city water. I've been in Miami almost 50 years. I've been drinking city water for 50 years and not died yet. So, you know, it's okay. But invariably, someone's paying for that city water, right? The parish or wherever I'm living. And bottled water, of course, it's a big industry. Natural right to water, to drinking water, it's a challenge. It's a big challenge. But like I say in the business world, the challenge is the opportunity, right? So how to make accessible drinking water to the population of the world. There we'll end it with a bioethical issue. Okay, folks, I'm going to stop here. You've been very patient, ran through the break because I want to take some time now for the biostatistics. But this is basically what I have. If you would please read this little handout, okay? And I'll send it electronically also because these are part of the challenges where bioethics can make a difference and find a niche on this, how to manage water that it becomes potable to the people of the earth. Okay, so if there are no questions or comments, either from the ones who are online, I'm going to actually pause here, pause the recording. So if you people want to stay online, I'm going to give a few suggestions with regards to the biostatistics course, all right? And also hear you out on whatever you have to say about it. So let me just pause and then I'll download it afterwards, as always, for the YouTube. Thanks again. God bless. Bye-bye.